Hi, today we'll be talking about taming tail latencies in Apache Pinot with Generational ZGC. Last year there was a great talk on what Generational ZGC was, so this talk will focus more on like a real-world application of Generational ZGC. My name's Chris. I've been working with Pinot at Uber for a little over 2 years. Brief agenda. So what is Apache Pinot? We'll talk a little bit about that, how we identified tail latency as a major problem and kind of the effects that we saw. A brief intro to ZGC, kind of a separation between the impact of a JDK upgrade versus ZGC, because for us, the two of these kind of went hand in hand. And then our results and key learnings. So what is Pinot? Shown on the right, Pinot uses kind of like a typical scatter-gather pattern where a query hits the broker, which sends it out to relevant servers that might contain potential like segments. Queries often aim to prune as many segments or servers as possible to reduce response times. In our use case, we try to take advantage of the scatter-gather for parallel processing. So we scatter to almost every server in most cases. And this provides or brings on some kind of like unique challenges. Pinot as a technology leverages indexes very heavily. And these indexes can have entirely different kind of like memory allocation patterns. So because ingestion and query share resources, optimizing GC for one of them could lead to degraded performance for the other. And then we'll also talk about a lot of the effects of generational ZGC. It was introduced with Java 21, and it has an emphasis on low pause times. So to give you some context kind of on our problem, the use case is like real-time log search and analytics on Pinot. So this is a screenshot of one of the ways that our engineers interact with Pinot, and it's through this kind of log explorer UI. Log search naturally has a very high ingestion volume. A lot of CPU and memory is used purely for ingestion. In our case, this is between 2 and 3 nines. And identifying that tail latency was a problem was also very difficult initially due to a few like kind of confounding factors. Because these are ad hoc queries, these are log queries, there is no like established P99 limit that we can abide by. And then even kind of like trend observation is really challenging because there's significant day over day or week over week variance. Data hotspots are kind of expected. Filtered data is almost never evenly distributed across nodes. And then it's hard to tell if like a performance issue is from a slow node or because the amount of data scanned on the node was very different. Because it is a new system, there is no baseline to compare it to. So we don't know if it's reasonable for a query to run in like 2 seconds or 5 or 15. And typically, I think when people are thinking of tail latencies, they're thinking of P95 or P99. These can be kind of attributed to the confounding factors mentioned previously. And seeing a, say, P99 of 1.5 seconds isn't like necessarily a red flag. When we started looking at like the P0 or median, it became pretty clear this wasn't expected. So the graph on this page is a histogram of latencies of this like very simple select query. And essentially what I did was I kind of probed the cluster running the same query like I think 2,000 times. And we saw this distribution of latency. So the fact that on average it was taking almost a second, and in the best case it was taking like almost 400 milliseconds, definitely pointed to a problem. Investigating this a little bit more, Pinot, the broker response contains information about every server that responded. And I kind of isolated the response delay here. And we can see that most servers respond in just 1 or 2 milliseconds, but there's like 5 really slow servers and 3 kind of slow servers. So the probability of having at least one slow server kind of caused that latency distribution on the previous slide. And then what this looks like at different fanouts. I think the visualization here kind of helps understanding. Usually our metrics are kind of, they distill it down to a single like series or course histogram. Here we can see that like even for like a two server fan out, over half the query or half the queries are affected, and for a four server fan out, sorry, for a two server fan out, over a quarter of queries are affected, and for a four server fan out, over half the queries are affected. And then this is just kind of a summary of what we saw. In my mind, this is kind of like wasted response time because the query itself is known to be very fast, but it's consistently taking this much longer due to the bottlenecks. And in this case, it was pretty straightforward to kind of correlate this to GC. So when you start searching about how to reduce GC pause times, I think one of the first things you'll see is some of the promises by like ZGC or Shendo or some of the other different collectors. Initially, I explored ZGC, and this was the non-generational ZGC in Java 17. It had a few goals, which were to reduce the GC pause time. So I think they publish under 10 milliseconds, to handle large heaps, which is pretty typical at Uber. I think host memory is still growing kind of year over year, so it makes sense to be able to handle these very large machines. There should be a minimal kind of like throughput reduction. So I think they had a 15% or minus 15% goal compared to G1. But one of the things we noticed was you could spend a lot of CPU to hit this goal. And then another minor thing is kind of like operational simplicity. Not having to tune GC when there's different workloads running is very, very helpful for us. So initially, this looked really good, just using non-generational ZGC with JDK 17, doing a little bit of testing, and this is the same kind of method as before. We're probing a cluster. We saw a very different case when we did our probing. So for the baseline, which was Java 11 and G1, we saw that long tail again going up to almost a second. And with ZGC, that tail was pretty much entirely eliminated. And then if we start looking at the kind of broker level, so this is not a single server anymore, but after the gather phase has happened, we still see the big improvement in the kind of like median and average latency. And then we also saw a small reduction in overall error rate. And at this point, this was looking very promising. But observing it a little bit more during peak hours, we noticed that even though the latency reduction kind of held true, the error rate had increased. And because our users are engineers, they're trying to debug with these queries. So it's okay if it's a bit slow, but we want to prioritize the error rate. So going kind of into evaluation criteria, what constitutes an improvement? For us, we couldn't make any compromises on error rate, but we wanted to improve the latencies. And looking into what actually contributed to these failures, they were mostly timeouts, and there's a few main reasons. One is like GC pauses can lead to timeouts. One query can spend a few seconds in GC, which impacts the success rate. With JDK 17 and ZGC specifically, we saw two other kind of factors that were contributing at those peak times. One is CPU exhaustion. So too much CPU could be spent on GC, and that would lead to timeouts. Scheduling queries would back up, queries would be kind of terminated before even being executed sometimes. And allocation stalls had kind of the same kind of effect here. So as queries would back up, they wouldn't get executed or they'd get killed. And it wasn't a very usable experience. At this point, I kind of started looking towards Java 21. I think even in G1, there's a number of improvements. G1 GC has like less memory overhead. There's a whole host of other things in the changelog. But one of the main things was generational ZGC was introduced. And this maintains separate generations for young and old objects. And the thinking was this could probably help us reduce that high CPU we saw from non-generational ZGC. So just a quick kind of comparison for pause time. JDK 11 versus 21 for G1. In JDK 11, we saw like that 1 to 3 second range for pause times. In JDK 21, it brought this down to between about half a second and a second. And then interestingly, ZGC or generational ZGC is also on this graph. But at 1 or 2 milliseconds, it's not really visible. I did a bit of CPU profiling as well at this point, and we noticed that with JDK11 we were seeing like 65 or 70% of CPU was just spent on GC, and it wasn't able to keep up with the default kind of like max pause time setting. Um, with JDK21, this reduced quite a bit. We only saw about 25% of CPU being spent on GC. And this still had the same kind of default like max pause time, which it still wasn't able to keep up with. But just this was telling us that like a Java version upgrade helps a lot. So the big takeaway here is to keep Java or keep the Java runtime at least up to date. Since the pause times still weren't acceptable, looking at generational ZGC, we actually saw an improvement in the CPU time spent here as well. So it's about 12% savings compared to G1. For us, we also had Z Proactive enabled, which increases CPU usage a little bit. And we use softmax seed size to kind of give us a little bit more back during or for memory uncommit, which helps out with some of like Pinot's other processes. We don't we're not using large page or huge pages or NUMA or anything, so there's a little bit of I guess left on the table here, but it's still a net improvement. Trying to do a little bit of kind of like degradation testing, because but before ZGC had looked like very promising until we had kind of like our peak traffic periods. I did this by kind of sending or increasing the QPS and sending queries until we had about like 100% failure. ZGC like pretty clearly showed lower throughput. We started failing queries very early, but generational ZGC and G1 failed at approximately the same time. The difference was with generational ZGC, we saw very low latencies. There were a couple kind of like application changes that were needed to kind of realize this. So one of the first ones was just reducing the state transition max threads. And Pinot uses Apache Helix as kind of like cluster management. So for example, when a server starts up, it has to load all these segments. Sometimes it rebuilds some of them. When we have too many of those parallel operations going on at the same time, we were running into a lot of allocation stalls and they start to compete. By reducing the number of threads here and reducing kind of that, I guess, kind of noise, we were able to improve our server startup time and we didn't get these kind of like random runtime spikes that would impact queries. The other main thing was Pinot has a feature that was contributed by LinkedIn, which is automated query killing for like very expensive queries. And it does this by tracking the heap usage per query as well as the overall heap usage of Pinot. If heap exhaustion is near, then we kill the most expensive query. And this gives a really fast recovery for subsequent queries. So in this graph, you can see that there's some query that triggered this huge heap spike. Maybe GC can't keep up with it. Maybe it just needs to use that much memory anyway. The effect is the same in both cases. The query gets killed, the heap drops very quickly, and we're ready to serve queries again. So the results from enabling generational ZGC. I reran kind of that initial probing test. The first graph is JDK11 using G1 in peak hours. We saw that kind of like distribution of latencies, and we also saw a failure rate that was non-zero. When we went to JDK21 and generational ZGC, we saw very, very consistent performance even on the broker level. So this is, again, no longer distribution of kind of server response times, but broker response times. And this shows us that the actual server response times are extremely, extremely consistent. And the other benefit that we saw shown on the right is just no failures. Since we are replacing kind of like a benchmark system, I thought I'd show some of the real user-facing results. In that first graph where we showed the UI that like users are interacting with, these are the queries that they're sending. So the old system, which we're replacing, which is powered by ClickHouse, was in green. And it's very consistent. And we initially had much higher latencies when trying to migrate to Pinot. After enabling generational ZGC, and you can kind of see when the rollout starts through the red line, the latencies drop quite a bit. And our daily kind of like P95 is improved a lot. In terms of resource usage, so a lot of this resource usage comes from the actual JDK upgrade, but we saw a roughly 50% CPU reduction from going from JDK 11 with G1 to JDK 21 with generational ZGC. And then also with Z proactive, so it'll proactively start, I guess, collection cycles. We're able to kind of return a lot of this memory back to the OS, and this is just kind of generally helpful. In terms of takeaways, I think JDK upgrades are super important. We saw that like even without generational ZGC, just using G1 and JDK 21, it brings overall big performance and efficiency improvements. Generational ZGC is also very beneficial, at least for our case, but also in general. We found the operational simplicity part is really hard to kind of express how much this can help, because with Pinot we have so many different index types. People are changing indexes, they're adding columns. All of these things contain GC patterns, and it's not super efficient if people have to go in and then do some GC tuning every time that's done. Being able to kind of have one GC that kind of self-tunes is very it simplifies kind of our day-to-day work a lot. And then one other big takeaway is constant probing. So sometimes identification is the hardest part. Solving the problem in this case was as simple as really just dropping in a new JDK runtime and changing the garbage collector. But figuring out what the problem was took quite a while. So having some sort of probing where the expectations are clear and kind of any divergence from those expectations can be seen, and then you can take an action, is really important. It kind of it just removes the uncertainty about like, is this query performing as it should or as it shouldn't? Is there an issue here? It tells you like very deterministically. I hope this was helpful and interesting. If you have any questions, I'd love to answer them or connect.